Okay, so our second young researcher of the day is Cristhian Garay from Universidade Federal Fluminense, UFF, and he will speak on real Weierstrass points of real algebraic curves of genus 4.
Thank you very much for the opportunity for being here. It's a really interesting conference. And I would like to take this opportunity to promote tropical geometry by showing you how to solve a problem in enumerative algebraic geometry. So the objective is to give an application of tropical geometry to real and enumerative algebraic geometry. So the ingredients for, first I will talk about a very general motivation in which this problem sits. Then I will give some words about the proof, and then some words about the geometry behind the proof, because the proof is really very constructive, but the geometry behind the proof is really, in my opinion, is really beautiful. So what I'm going to use for this introduction is I will consider a smooth real algebraic curve of genus G with an empty real locus. And in other words, this is a pair of a complex smooth projective curve together with another piece of information, which is an anti-holomorphic involution, such that the fixed locus of this involution on the curve is non-empty. So the image that we get is picture a traditional smooth curve of genus G. Then inside this curve, you get some circles, some special circles. And you have an automorphism that interchange in some way the upper part and the lower part. And this part is fixed by this sigma. And then the second piece of information is a real linear series of degree D and rank R defined on this curve. This is an algebraic line bundle, but induced by a divisor. But since I have this involution, I can make sense of what is a sigma stable divisor or a divisor fixed by sigma. And you need to see that it is something like this. It has some pairs of conjugated points with the same multiplicity, both of them, and some points on the fixed part. So these line bundles are special because the inflection divisor is stable with respect to the involution. The inflection divisor are some special points on the curve which have a special behavior with respect to the dimension of series that vanish on them. There are always a finite number that just depends on the degree, the rank of the real linear series, and the genus of your curve. And this is the number. They may need to be counted with multiplicity. But the point is that since this divisor is sigma invariant, you can express it as a part which is on the real part and the part that is point together with its conjugate. The problem that we want to study is what can we say about the weight of the real part. So this is a very general problem. You can state this problem to find the maximal number of real points that you can make on a curve, denoted by this. Well, for the real part, this problem depends on more parameters, in fact. But the point is that you want to see how this number of real points compares to the total number of inflection points. And the point is that we don't know many situations. There were some results by Felix Klein, which are rather classic, and he studied the plane case in all degree for smooth curves. He says that the number of real points that you can have on a smooth curve of genus G and degree D plane curve is at most 1/3 of the total amount of inflection points. Then we have work in genus 0 at the beginning of the 2000s, and they showed, Mukin, Tarasov, Varshenko showed that for any R and D satisfying this, on a genus 0 real curve with non-empty real part, there is no restriction. You can always find a real linear series such that all its inflection points are real. But the problem is that for this problem of finding curves with a lot of real Weierstrass points, these were all the results. So the next cases in this philosophy would be genus 1, and we made some progress for genus 1. When the linear series is complete, we showed that you have a linear expectation of real Weierstrass points with respect to the total amount, which is quadratic. And we made another contribution for rank 3. So this is about spatial curves, and in the case of the hyperelliptic embedding of a non-hyperelliptic curve of genus 4. So in the particular case, when you use the canonical series, these are called Weierstrass points. And I will give you the result in genus 1 to give you a taste about real algebraic geometry. So you take a smooth elliptic curve and a complete linear system there. So the total number is d squared, and your real curve may have either 0D or 2D points, real points. And in fact, these are all the possibilities. Either your real part is connected, so you have D points, and if you connected components, you have two connected components. It depends wholly on the parity of your divisor. So the best that you can do is 2D points, and it happens when you restrict your divisor to both connected components, you have parity. You have pair parity in both of them. So this is the kind of results that you get in real algebraic geometry, enumerative algebraic geometry. And we want to use this result to construct a genus 4 curve with many inflection points. We already know that we cannot make better than 2D, than 2D real points. So this is a general result for any complete linear series on any real elliptic curve. So I am going to give an idea of the construction, and finally I will talk about the philosophy behind that. So the first lesson is that tropical geometry needs hypersurface inside toric varieties defined over some exotic fields of characteristic 0. These fields are known as non-Archimedean, but nevertheless they are algebraic. They may be algebraically closed, characteristic 0. So we need to prove that we need to generalize this classical result for complex curves, that any smooth non-hyperelliptic projective K-curve of genus 4 is realized as a smooth complete intersection of a cubic and a quadric in the projective space. This is done because you want to work with a hypersurface in a toric surface. Then what we do is to choose conveniently the quadric as the quadratic cone. Because this is a toric surface, it's normal, it has a singularity, but it is associated to this convex polytope. So the complete linear system of this polytope gives you, this is the weighted projective space, this gives you an embedding of this toric surface as a rational normal cone inside the P3. So next we want to consider sections of this embedding of this toric variety inside the P3. But we can use this linear system to take the curves. Instead of working in the space, we can work in the toric variety. So when we work with sections of degree 2, we find a very interesting result is that if you choose the polygon to be this guy, then this is going to give you a conic section here, and when you plug it back to P3 using the canonical linear system, you get an elliptic curve on the tree space. But what is interesting here is that you get the maximal amount of real inflection points as long as these two mild conditions are met, which is that this central coefficient has to be non-zero and the product of the diagonals have to be negative. So this is almost combinatoric. There is no conditions about the coefficients, just the signs. If you choose the sign satisfying these two properties, then your curve has maximal inflection. So if we paste 4 of these guys forming a degree 3 section, the resulting curve is going to be degree 3 inside this degree 2. So the result is a curve of genus 4. And we can expect to have 4 points here, 8 points here, 8 points here, and 8 points here, right? Because this is the philosophy of tropical geometry. And in fact, this is what happens. If you consider this, what is called patchworking polynomial, and you compute the number of real inflection points of this curve, it turns out that it has 30 inflection points. And the philosophy is this. So you start by looking at the dual graph of this polytope, which is called a tropical curve. This tropical curve represents the skeleton of a semi-stable model for your curve. And this, in turn, is the dual graph of the special fiber of some semi-stable degeneration. And limit linear series takes you from a smooth object to a singular object, and tropical geometry is the opposite way. Takes a singular object and somehow gives you a global smooth object such that the local information that you had on the red part, which is the real part of your curve, is preserved here. So we managed to have all the points here. They passed through the genetic fiber, but we got 6 more points. And I think that's all. Thank you.